Hello, welcome everyone, and welcome to this particular video of mutually exclusive events. So fundamentally, I wanted to make a video on addition theorem of probability. So the mutually exclusive events play a very important role when I talk about addition theorem of probability. So I'm trying to complete that lecture series on probability theory to take you all through numerical questions and everything. So let's understand what the mutually exclusive events are. So I have already mentioned in my previous videos that events are also known as outcomes. So events can also be considered the outcome of any particular experiment. So they can be considered as outcomes of any particular experiment. So two events A and B are said to be mutually exclusive if they cannot occur at the same time. That means they cannot occur simultaneously. So if certain examples I have taken, A is an event getting head on toss of a coin, B getting a tail on the toss of a coin. So if you toss a coin, either you are going to get head or you are going to get tail. It cannot happen that you can get tail as well as head at the same time. So A and B here in this particular case are known as mutually exclusive events. Same way, if you look into the other example, getting odd number on a dice, on the roll of a die, it is an event A, and getting an even number on the roll of a die is event B. And of course, they cannot happen at the same time, because if you look into the even numbers on the die, they are actually 2, 4, 6. And if you look into the odd numbers on a die, they are actually 1, 3, 5. So if you're going to roll a die, either you're going to get an odd number or you're going to get an even number. So A and B here again, A and B are mutually exclusive. A and B are mutually exclusive. Let's talk about the third particular case where I'm saying event A is defined by getting an odd number. So in this case, I can get either 1 or 3 or 5. And the second case is getting a 3. So if you look into both these things, then they can happen at the same time. That means if I flip a die and I get a 3, then I also get an odd number and I also get 3. So in that case, A and B are not mutually exclusive. So the concept is very simple. If two events, you just need to see the defined events, and if these two events can happen at the same time, then they can be known as non-mutually exclusive events. And if they cannot happen at the same time, they should be understood as mutually exclusive event. Another example could be if event A is defined by getting a king out of the pack of cards, and event B is defined as getting a red card. So if I get a red card and a king, then both the events can happen at same time, and that's why they cannot be considered as mutually exclusive events. So let's move and let's understand exactly some things like symbolically I have theoretically told you. So if I just go symbolically, then something like this, just excuse me for my spelling mistake if it is there. So if, mathematically, if I want to write it, A intersection B. So this definition comes from the set theory. I'll just make you understand is a phi. And this can also be understood as a null set or a void set. If you have a little knowledge of null set, or you can also call it as a void set. So if A intersection is B is phi, in that case then A and B are mutually exclusive. Other way around, if I want to use a Venn diagram, and in that case you can simply show it that let's suppose this is the entire universal set, this is event A and this is event B, and you can simply see that there is nothing common between A and B. So if I just want to write, so intersection is in probability theory sometimes can be understood as and, so A and B. So if you look into A and B, there is nothing in common. There is no element which is in common. So in that case, I can write here that A intersection B is phi. That means null set. How do you represent null set or phi? Yeah, a little recall of the set theory. It is represented like this. That means nothing in this particular set. So A intersection B is phi, and that's why you can say that A and B are mutually exclusive. If I move little into the probability theory, then you can simply write it like this: probability of A and B, that means probability of happening of A and B is an impossible event. That means probability of happening of both the events together is 0. Or you can simply write it this way: A intersection B is 0. This is another way to write it. Or you can simply write it probability of A and B is 0. So you can simply understand if there are two events are there and there is nothing in common, then those particular events are known as mutually exclusive. So I have told you three different ways to represent mutually exclusive events. One is, of course, the theoretical definition, in which I have told you that if two events cannot occur simultaneously at the same time, they can be understood as mutually exclusive events. And I used a little of set theory to make you understand what do you mean by mutually exclusive events. And of course, from here on, you can understand if probability of happening of two events at same time becomes 0, then these particular events can be understood as mutually exclusive events. This concept will be is going to be used as a lot more in addition theorem of the probability. That means addition theorem results will be dependent on whether the events are mutually exclusive or not. So I'll just little bit give you a little extension of this particular thing of this set theory example here. So if let's say there is a set A and which contains something like 3, 4 and 9, and there is a set B, then in that particular case it is considering, let's say, 1 and 0, two elements in it. And if you try to draw a Venn diagram out of this is universal, this is set A, and it is exactly containing 3, 4, 9, and this is set B, which is containing 1 and 0, right? And what is in common? What is a common element between them? Nothing, null. Nothing is common in between them. So A intersection B can be written as phi, a null set. On the other hand, if I have one more subset of one more set C, and it is exactly something like 2, 4, 10, then the story is a little different. Now if I try to draw A and C, so it is going to be something like this. I have A, I have C, this is universal set, and I got in C 2, 10 and 4 is going to come here, of course in the common area, 3 and 9. So in that case, if you see A intersection C or A and C, they have 4 in common, a singleton set. That means A and C are not equal to phi, they are not empty. The intersection is not empty, it is equal to, not equal to phi. So this is example of mutually exclusiveness. This is not mutually exclusive, depending on set theory. So that's how it can be understood. If there are two events which have nothing in common, they are mutually exclusive. If they have certain things in common, they are not mutually exclusive. Thank you. In next video, I'll be discussing theorem of addition theorem of probability, and that's it. Thank you very much.